Alright guys, so in this video we're going to go through three integrations by substitution, an easy one, a medium one, and a hard one. You can see the three integrals in your screen. And I gotta say the first one could be easier, but I didn't want to make it too easy, so it's easy slash medium, let's say. The second one, which is medium, it's kind of hard, so I guess it's medium slash hard. And the third one, well, the hard one does require something that you're probably not familiar with, but the idea is that after this video you're gonna be more comfortable with this type of substitution. Just to give you a spoiler, we call it integration by trig substitution. However, the idea is not to go through all types of integration by trig substitution. Okay, we're not going to do that today in this video. However, I wanted to give you one example of what it looks like. Okay, so these are usually trickier integrals, and all of them, as mentioned before in the beginning of the video, they require substitution. So let's start with the first one, the easy one. Easy slash medium. Now over here we have the integral of x squared minus 1 times cosine of 3x cubed minus 9x dx. Do notice that 3x cubed minus 9x is the arc of cosine. It's inside the cosine. So in this next step, what we need to do is to figure out what u is. It all boils down in integration by substitution. It all boils down to selecting an appropriate u, an appropriate substitution. You can go a few ways here. Some of them are actually just one of them will work, but you could try other ones which wouldn't work. For example, calling x squared minus 1 u, or the entire cosine of 3x cubed minus 9x u. None of these would work. The substitution that works is 3x cubed minus 9x as u. Now you might be wondering, okay, got it, but how can I always get the substitution right? And well, I have some good news and some bad news for you. So the bad news is there's no process that you always use in order to always get this substitution right every time. It doesn't exist. But the good news is there is something that you can think about when trying to figure out what u is. You want to look at this integral and say, I need to find a function which we're calling u, and its derivative will be somewhere there, or at least a multiple of that derivative, which is going to be more clear in a minute. So for example, if we choose u to be x squared minus 1, du is 2x dx. We wouldn't be able to replace, for example, 3x cubed minus 9x neither by u or du or nothing actually. So this is not the way to go. However, if you choose your u to be 3x cubed minus 9x, your du, which by the way, it's not something that you choose, it's a consequence of the choice that you made before. Du is the derivative of u. Du is equal to 9x squared minus 9 dx. And by the way, you could have written this as du dx, which is the derivative of u with respect to x, as 9x squared minus 9. This is equivalent to the blue one. And when you get to this, you might say, all right, but I can replace whatever's inside the cosine by u, but I don't see 9x squared minus 9 dx anywhere in this integral. But the key thing here to do is to factor out a 9 from the right hand side, which shows us we didn't get x squared minus 1 dx as we wanted, but we got 9x squared minus 9 dx, which is fine. This is 9 times x squared minus 1 dx, which means that du over 9 is our x squared minus 1 dx, which makes us able to replace x squared minus 1 dx by du over 9. So on the next step, our integral becomes du over 9, which is this guy over here. And let me actually color code it a little bit different so we can see where u and du, where they are. And we also have cosine of u. And before we continue this, you might be thinking, hey, but I actually learned this in another way, in a different way. And I've seen students do that multiple times. So if it helps, you can run the substitution like this. Let me call this method 1, and let me show you what method 2 will look like before we actually finish this integral. I copied the integral from above, and after selecting u, you may differentiate u with respect to x and maybe you write it like this, or you leave the dx to the right hand side. But the idea is you have your 9x squared minus 9, which means that du is equal to 9x squared minus 9 dx, and this is what makes this process or this method a little bit different. You will rewrite your dx as du over 9x squared minus 9, and you replace it over here. As you see, in a few steps, you get to the same place. So both of these methods, they work. So you have the integral of x squared minus 1 cosine of u, and then you multiply that by du over 9x squared minus 9. Now, knowing that you can rewrite this as 9x squared minus 1, you can cancel out the x squared minus 1 with this, and on the next step, you get to the same place, to the integral of cosine of u times du over 9, which is exactly where we stopped in the previous method. So let's continue the solution in the previous one. 1 over 9 is just a constant, so we can move it outside the integral. So we have cosine of u du, and we know that the integral of cosine, which is the function that differentiated gives us cosine, is sine. So we have sine of u times 1 over 9 plus c. Now, do we stop here? We don't, because we made up this variable u. We need to go back to the original variable, which is x. What does u represent? U is 3x cubed minus 9x. Therefore, we have 1 over 9 sine of 3x cubed minus 9x plus c. Now, this is the solution of this exercise. Now, we can move to exercise medium, or exercise number 2. All right, so this is the second exercise. You realize quite fast why this is considered a medium/hard exercise. Now, we have two functions here, two trig functions. We have sine and cosine. We can try to replace u or replace cosine by u, which would make this into a u, or replace sine by u. Why is replacing sine better by u? Because du is negative sine of x. So we have our du dx, by the way. So we have our du over here, or negative du actually over here. But we have all these things in the denominator that we couldn't substitute. So it doesn't work. Is there some guessing and checking when integrating by substitution? Yes, 100%. You will feel more confident, more comfortable as you work in multiple exercises or with multiple exercises. But to be honest, there's still some guessing and checking, especially for the harder types of exercises, So let's replace u, or replace sine of x by u, which means that du is cosine of x dx. And let me color code this again. We can see our du over here, and we can see a bunch of u's in blue, giving us the integral u du over u squared minus u minus 2. And then you might say, hey, it didn't work because this looks awful, right? And well, I agree, it does look awful, but it did work because right now we can use another integration technique that will take us from this hole, from this gigantic problem, which is integration by partial fractions. And that's exactly why this exercise can be classified as medium/hard, because we have two techniques here. We have substitution, but we also have integration by partial fractions. So lots and lots of fun ahead of us. Let's factor out the denominator first. Factor out this quadratic. What is u squared minus u minus 2? We can factor this as u plus 1, u minus 2. So this is the integral that we have. And we are going to break this down into partial fractions. So let's enter the realm of partial fractions. How do we convert u over u plus 1 times u minus 2 into two fractions? And we know it's 2 because we have two binomials in the denominator. Hopefully you're familiar with this, but let me just give you the shorter version. So we have this being converted into a over u plus 1 plus b over u minus 2. If you haven't studied integration by partial fractions in school, you will eventually in HL. And if you didn't, you might as well just learn it now. So it all boils down to comparing these left and right hand sides. We're going to have on the left hand side the same thing, but on the right, if we want to write the right hand side with a common denominator, this denominator will become u plus 1, u minus 2, and the numerator will be a u minus 2 plus b u plus 1. Now, given that the denominators, they're the same, we're not going to be looking at this. We're going to focus on the numerator. So u is a u minus 2 plus b u plus 1. The whole idea is to find these numbers that are usually integers or rational numbers, a and b. And the fastest way to do that is to substitute u by some number. And we're not talking about substitution in the sense of integration by substitution. We're not talking about that. This is algebra. We just replace u by a number which is going to help us get these coefficients the fastest way possible, right? What are these numbers? Well, we can replace, for example, u by 2. And when we do that, we have 2 equals a 2 minus 2, which is just 0, plus b times 3. So 2 is equal to 3b, therefore b is 2/3. And then we do the same for u equal to -1. We have -1 equals a -3 plus b times 0. So -1 equals -3a, so a equals 1/3. Therefore, this integral becomes the integral of a over u plus 1 plus b over u minus 2, given that u over u plus 1 times u minus 2 is equivalent to this. Changing the integral like that will help us find, or will help us integrate. There are going to be lns, natural logs, in the answer. And it will only be possible to find them if we actually break it down using integration by partial fractions. So that's the value of this method. So let's copy the constants a and b here, and we have u minus 2 over here. We can break this integral down into 2 and also move the constants outside. So we have 1 over 3 ln of the absolute value of u plus 1 plus 2 over 3 ln of the absolute value of u minus 2 plus some constant c. We cannot leave the answer like this because we created this variable u. We need to go back to x. Do remember that u is sine of x. Therefore, as the final answer, we have 1/3 ln of sine of x plus 1 plus 2/3 ln of sine of x minus 2 plus c. Now, can I rewrite this expression moving the 1/3 to the exponent and the 2/3 to the exponent of sine of x minus 2? Yes, we can do that, but let's just stop here because the purpose of the video is just to apply substitution and other integration techniques. So this is fine. Let's move to the hard one, the one that requires integration by trig substitution. All right, so the hard integral is the integral of dx over x squared root of x squared minus 1. As I mentioned before, this is an integration by trig substitution, which means that we're going to replace x by a trig function. Is it intuitive to know that, to realize that? Absolutely not, but it does make a lot of sense once you understand the process. The idea is to expose you to this type of integration technique, which is not in the IB AAHL curriculum, but I've seen multiple times it being used when the examiner suggested this type of substitution. So you don't need to know just by looking at this that this exact substitution works. They will give it to you, right? But I think it's important to know, it's important to understand, it's important to be familiar with it. So I've seen in other IB math exam questions. Therefore, let's just tackle it to understand how it works, okay? By the way, I will record a series of videos with just integration by trig substitution. In those videos, I'll explain exactly how to look at this and to distinguish whether you should substitute it by sine, secant, or tangent. These are the three substitutions that we use. In this case, we are going to replace x by secant of theta, which again, it's not intuitive. But let me show you why it works like a charm. If you call x secant of theta, your dx, by the way, is the derivative of secant, which is secant times tangent d theta. What we get inside this root is secant squared of theta minus 1. You might, and you should, recognize this as being tangent squared of theta. And on the next step, we're going to simplify it, crossing out the root with a square. Outside this root, but still in the denominator, we have secant squared, given that we have x squared. And in the numerator, we have dx, which is secant theta tangent of theta d theta. Now, as you realize, there are lots of things that we can cancel out. We have, for example, this tangent, which simplifies with the tangent from the numerator. We have one secant, which we can simplify as well. And everything boils down to the integral of 1 over secant of theta. And you might be wondering, okay, but I don't know what the integral of 1 over secant of theta is. And let me say that you do know, given that secant of theta is 1 over cosine. So what you have in front of you is cosine of theta d theta. And the integral of cosine, well, that is just sine of theta plus c. Do we stop here? Absolutely not. We do not. We need to go back to the initial variable, which is x. How do we do that? Let's take a look at the substitution that we used. And this is where integration by trig substitution becomes even more interesting. We have a secant of theta, which is equal to x. So if you draw a right triangle and let theta be this angle right here, the secant of this angle is equal to x. What is a secant? Well, a cosine is adjacent over hypotenuse, which means that a secant is hypotenuse over adjacent. Given that this is x, and you can represent x as x over 1, the hypotenuse is x, and the adjacent side is 1. Wait, I didn't get it. Go back. So here's the idea. Secant is hypotenuse over adjacent, given that cosine is adjacent over hypotenuse. Therefore, the hypotenuse is x, and the adjacent side is 1. If you want to complete this right triangle, you can by using the Pythagorean theorem. You should, actually. This is equal to x squared minus 1. You can verify that using the Pythagorean theorem, as I mentioned before. Therefore, sine of theta, which is opposite over hypotenuse, it is equal to the root of x squared minus 1, which is the opposite side, over the hypotenuse x. And then we have a plus c, plus constant. Therefore, this is the integral of this. How can we check every time if we integrate it correctly? Well, you can differentiate, and if by differentiating you go back to this, that means that the answer is correct. But the answer is correct. All right, so these were the 3 easy, medium, hard exercises on integration by substitution.